One of the major problems facing the oil industry today is that of mineral growth occurring in hydrocarbon-producing well bores. Many wells already have a significant growth of scale, but the problem is growing as the breakthrough of injected water is becoming more common and the scale itself is becoming more tenacious. The primary effect of mineral growth on the tubing is to lower the production rate by increasing the surface roughness of the pipe and reducing the flowing area. The driver pressure therefore goes up and production goes down. If the mineral growth increases, then access to lower sections of the well becomes impossible, and ultimately growth in the tubing itself will bridge over completely. As a reservoir becomes depleted and water breakthrough occurs, the water, which is often high in dissolved minerals, enters the well and starts to flow up through the pipe. As it rises, a combination of cooling and the drop in pressure saturates the liquid. The salts, which had been dissolved, come out of solution and scaling on the tubing begins to develop. A more severe situation arises in the case of the breakthrough of injected seawater, which is often high in sulfate salts, and its mixing with formation water containing a high percentage of other salts can result in barium or strontium sulfates being deposited. These scales are very hard to dissolve. There are two conventional methods for removing these scales. The first is chemical, but involves very long soak times, in some cases up to 60 hours. The second is mechanical, using milling tools, but all too often this leads to tubing and jewellery damage, or failure of the cleaning tools. So, what are the solutions? Scientists at Schlumberger's research centre in Cambridge have been developing a new abrasive jetting technique to clean both tubing and wellbore equipment without damage to the steelwork or jewellery. In order to test jetting techniques under realistic conditions, a full-scale test facility was built here in Cambridge. This JCR is powered by a 750 kilowatt pump and can simulate jetting with a back pressure of up to 5,000 psi and realistic nozzle pressure drops achievable in coiled tubing operations. Our first step was to undertake an in-depth study of jetting performance. The most critical finding was that the performance of a jet under downhole conditions was significantly different to that encountered on the surface. In surface conditions, without back pressure, small bubbles form in the jet and collapse on the target with a large erosive effect. This process is known as cavitation. At downhole pressures, however, the formation of these bubbles, as well as the erosive cavitation effects, are suppressed. Typically, a jet is 4 times more erosive close to the surface than in downhole conditions. In other words, a jetting scale removal system may work effectively in a yard test or in a shallow well, but under realistic downhole conditions, the performance may be impaired considerably. Tests of scaled tubing recovered from a producing well show that a pure water jet without the use of dissolvers is almost totally ineffective. Adding a small concentration of sand to the fluid changes the character and performance of the jetting system. A sand abrasive jet will remove the scale from the tubing, but it will also cut the tubing steel, running the risk of puncturing the production tubing and destroying the integrity of the well. To devise a safe jetting system to remove the scale but retain the integrity of the tubing, a detailed study of the interaction between the abrasive particles, the target scales, and the tubing steel was made. And, since the behavior of individual particles is also critical, we built a particle impact tester to study collisions and high-speed particle impacts. In the erosion of ductile materials, such as tubing steel, the shape of the particle is critical. For example, a sharp sand particle will plough into the surface and shave away the steel, causing high levels of damage. However, a hard spherical particle impacting the surface will still deform the surface, but will leave a spherical crater and cause much less damage. In the case of scale and other brittle materials, the abrasive shape is not important, as the surface is removed not by the ploughing action of the abrasive, but by the impact process which causes nucleating networks of fractures through the material. The use of spherical particles is not the total solution. Here we see the impact of glass beads on a mild steel target. Repeated impacts of multiple particles will result in high levels of fatigue on the surface and levels of erosion of the tubing steel which are less than those of sand, but still intolerable in terms of the tubing integrity. Another key property is the fracture toughness. If the abrasive is too weak or the surface too strong, then the impacting particle will shatter into fine dust and cause no damage to the scale. The result of this scientific study was to design an abrasive material with all the right properties to remove the scale from the tubing without damage to the steel surface. This material is sterling beads. The performance of these abrasives on production tubing is to remove the scale and leave the tubing in a clean and undamaged condition. The development of this technology has enabled a new generation of tools to be developed for cleaning tubing. But of course its success can only really be gauged by its performance in a scaled well. One of our clients used the sterling bead system to remove aragonite, a form of calcium carbonate. All other systems had failed completely, and 12 tungsten carbide mills were destroyed in 4 days. So what happened when they tried using the sterling bead system? It worked. It cleaned 425 feet of tubing at between 30 and 90 feet per hour. And when the tubing was finally recovered from the well, the scale on the section treated with sterling beads had been completely removed. Furthermore, 95% of the plastic coating which had originally lined the pipe was left intact. So, with the help of detailed material science research, we have successfully developed a new technology which can solve an existing oil field problem, as well as bringing new services and benefits to our clients.